Okay, so this is question number 2. Question number 2 starts with y equals e to the power of x times sine x. They define a function. Part A says find an expression for dy by dx. Okay, so this one's not so bad. I've kind of separated them into different parts just so we have some space. So part A says find dy by dx. Here again, you have a product of two functions, so you have to use product rule. Product rule says derivative of the first times the second plus the first times derivative of the second, and that's going to be cosine x. Here, if you want, you can factor out e to the power of x, and then we get this. Okay, and that's about it. Part B says, so I'll move this to the side here. Part B says find the second derivative, show that it is 2 times e to the x times cosine x. By the way, the reason that they're giving you a show question here, they didn't have to, is typically in section B, because subsequent questions, like their answers depend on previous answers. A show question is a way for an examiner to tell you that, like, hey, this is the answer you should be getting. In a way, they're guiding you through the problem and making sure that you don't mess up question part B, because if you do, then subsequent answers will be wrong. So part B here is just a way to just make sure you're on the right track. Yeah. Okay. So to get the second derivative, we take the derivative of the first derivative. Derivative of that is going to be derivative of the first, which is e to the x, times the second. Second function here is sine x plus cosine x. And then plus the first. That's going to be e to the x, times derivative of the second. Now here, the derivative of sine x is cosine x. And then the derivative of cosine x is negative sine x. So you get something like that. Okay. Now here you might notice that once we expand here, so if we expand, we get e to the x sine x plus e to the x cosine x plus e to the x cosine x plus, minus e to the x sine x. Okay, so you might notice here that there's a cancellation. E to the sine x, e to the x times sine x cancels with this, and then what you're left with are actually two of the same terms. Okay, so you can add those, you can group those together. So you'll get 2 e to the x cosine x, and as required. Okay, so question's asking for us to show that the second derivative was equal to this. Okay, so if we go back up, the answers match up. Okay. Next question, consider the function f defined by f of x equals to e to the x times sine x, and x here is between 0 and pi inclusive. Given the graph has only one stationary point, okay, so they're telling you there's only one stationary point. Show that the function f has a local maximum when x is 3/4 of a pi without graphing the function. Okay, so they want you to show that there's one stationary point, okay, and that stationary point, they want you to show it's a local max. Okay, so we'll need the first derivative. The first derivative here, we had it from earlier, so I'm just going to steal that from earlier. We had that was right here. And if we want the stationary point, we need to set this equal to 0. And this will be equal to 0 when sine x plus cosine x is 0. The reason for this is e to the x is positive for all x. Okay. And then we can divide through by cosine x. If we divide through by cosine x, we get 0 equals tan x plus 1. That means tan x has to be equal to negative 1. Okay. And now at this stage, if you want, you can draw it yourself like a diagram. The tan function will be negative 1 when the ratio of the x to y coordinates, y to x coordinates is negative 1. So that can be like this. You might have a situation like this. You might have a situation like this. Okay. Both of these points here, these points, both of them have a ratio of negative 1. And so the tan of this angle, and this angle will be -1. Now in this case, I think they give you an interval. The interval is from 0 to pi. So, and they tell you there's only one stationary point. So the angle that they're looking for in this case is this angle. You can exclude this angle because it seems to be negative. Or if you want to measure it in the positive direction, it's going to be larger than pi. Okay, so this angle is the only angle that works between 0 and pi. Okay, so that means that x must be equal to, that's going to be 3/4 of a pi. Okay, because the reference angle there is 1/4 of a pi. And the reason here is x is between 0 and pi. Okay, so that's why it's the only solution there. Okay, now what we need to do is we need to show that this function has a local max value when x is 3/4 of a pi. For this, you can just make a sign diagram. So you could say f prime of x has a sign diagram. And maybe I'll do from 0 to pi. Okay, and we know that at 3/4 of a pi, we have the derivative is equal to 0. So what we need to do is we need to test the value between 0 and 3/4 of a pi, and between 3/4 of a pi and pi. I'm going to do this kind of like on the fly, like I'll explain my thought process. But when you guys do this, you have to show the calculations. The reason is because it's a show question. Okay, so between 0 and 3/4 of a pi, pi over 2 is a nice value. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. This is always positive, so that's going to give you a positive value. Between 3/4 of a pi and pi, you could do whatever you want. Maybe you could choose like, I don't know, like 5/6 of a pi, something like that. Okay, 5/6 of a pi. If we plug that in, so sine of 5/6 of a pi is going to be -√3 over 2. Cosine of 5/6 of a pi is going to be, sorry, that's wrong. Sine of 5/6 of a pi is actually a half. Cosine of 5/6 of a pi is -√3 over 2. Okay, so that's going to be negative in total, and then that's always positive. Okay, so then we have negative. And so you would show that working, but basically the sign is changing from positive to negative, so the original function is changing from increasing to decreasing, so therefore local max at x equals 3/4 of a pi. Yeah, okay. Okay, part D is asking us to find the x-coordinate of the point of inflection of the graph of f. And then part E is saying sketch the graph of f, clearly indicating the position of the local max point, as well as the point of inflection, as well as the intercepts. Okay, so it's kind of asking for a lot. I'm going to do part D first, and then we'll do part E right next to it. So part D says we just need to find the x-coordinate of the point of inflection, so we can find the second derivative, and then set the second derivative equal to 0. So we get something like this. Now, 2 times e to the power of x is always positive. For all x. Okay. And then cosine x is going to be equal to 0 when x is equal to pi over 2. Okay. And the reason for this is, remember, x is between 0 and pi. That was defined earlier. They said here, somewhere here. Yeah. Okay, so the function's only defined in this interval. Okay, so that's it. I think that's it. Like they're just asking you to find the point, the x-coordinate of the point of inflection. That is the x-coordinate of the point of inflection. The second derivative is only 0 at one spot, and that spot happens to be the point of inflection. Now in this case, you can also verify it using a graph. So on your GDC, you can kind of verify that pi divided by 2 kind of looks like an inflection point. Okay, from earlier, we also know the local max is this. Here, I forgot to mention this in the video, but the x-coordinate we found earlier from part C, And then this I just found by plugging it into a GDC. Since the question says nothing about an exact value, a value to 3 significant figures is fine. Okay, and that's acceptable. So part E says sketch. So I'll do part E here. I'll do a sketch quickly. On your sketch, question says that you need to mark in your local max point as well as the point of inflection and the intercepts. Okay, so if you look at your GDC, if you graph this in your GDC, you're going to get something that looks like this. Something like that. Now, the GDC is maybe not going to tell you the intercepts. I guess you could use the GDC to kind of figure that out, but we don't really need to do that. I think we can do a little bit of analytic thinking to determine the intercepts. The function that we're dealing with is y equals to e to the x sine x. Okay, let me just verify that that's correct. Yep. So e to the x sine x, this part's always positive. E to the x sine x will be 0 when sine x is 0. Sine x is going to be 0 when x is 0, and when x is pi. So you don't really need the GDC to be able to figure out these coordinates. I think you can do that without a GDC. The local max value here, we know it's 3/4 of a pi, comma 7.46. Oops. And then the only thing left now is somewhere in between. You're going to have your inflection point. The inflection point is going to have a, my scale was kind of off. Sorry about that. My scale was kind of off here. Let's fix that. So maybe the inflection point somewhere here. Okay, so to find the y coordinate, you could just use a calculator, or you could just take this x coordinate and kind of plug it into the original function. So when you do that, sine of pi over 2 is going to be 1, and then e to the power of pi over 2 is just going to be e to the power of pi over 2. Okay, or you could just simplify this on a calculator. Okay, so that's part D and E.